Gold is made in Kirkland Lake, a mining town in northeastern Ontario, Canada. The area is known for its rich gold deposits, with over 30 mines producing more than 47 million ounces of gold. Currently, there is one operating mine called Macassa, run by Kirkland Lake Gold, which has poured 5 million ounces of gold. However, extracting the gold is a challenging task due to the over 5,000 feet of solid rock that separates the surface from the gold deposits. Miners descend over 4,500 feet underground to reach the gold deposits. They travel through drifts, which are large tunnels, to reach their work sites. Geologists collect rock samples by drilling deep into the rock using diamond drills. These core samples are examined to determine the direction for further drilling. Engineers then plan a specific drilling pattern, and the miners drill holes in the face of the drift accordingly. These holes are loaded with explosives. Once everyone is safely back on the surface and the tunnels are clear, a controlled blast occurs, extending the tunnel by about 10 feet. The muckers, who are responsible for removing the debris from the blast, come in and clear the area. Some of the muck removal processes are even controlled remotely from the surface. The muck, or broken rock, is then separated, and the ore containing the gold is identified. After the muckers have cleaned up the area, miners reinforce the tunnel with screens and rock bolts using tools such as the jackleg drill and stoppers. The ore is transferred from the muck area to the ore passes, where trucks are loaded from chutes. The muck is then hauled to the ore pass rock breaker, which processes the muck into 16-inch squares. The ore is sent to the ore pass and loaded into a skip at the loading pocket. From there, the ore is transported to the surface via the shaft. It's interesting to note that Clayle Gold's Macassar mine was the first company in Canada to use battery-powered trucks, reducing emissions, and taking up a smaller footprint compared to diesel trucks. The batteries of these trucks are charged in an underground charging station. Once the ore reaches the surface, it is crushed into pieces about 4 inches in diameter using a jaw crusher. The crushed ore then travels on conveyor belts to other crushers that further reduce its size. The final crusher reduces the ore to a size of 7/16 of an inch, similar to a Cheerio. From there, the ore is sent to the mill via a conveyor belt and dumped into the fine ore bin, which can hold 1,600 tons of ore. The ore is fed into a grinding mill, which contains steel balls that grind the ore to make it smaller. After grinding, the ore goes through another grinding mill with smaller balls to further dry it into a finer slurry. A cyclone separates the larger pieces from the finer pieces, and the finely ground ore, similar to flour, is then transferred to leach tanks. In the leach tanks, the ore is mixed with chemicals that extract the gold from the ore. Once the gold is removed, it is heated and mixed with chemicals to purify it. The purified gold is then dried in an oven overnight. By morning, the gold takes on an ash-like appearance. To further process the gold, it is mixed with chemicals and poured into a furnace heated to over 1,000 degrees Celsius. The gold becomes molten and separates into matte and slag. The slag, which contains waste materials, is poured out first as it floats on top due to the gold's heaviness. The remaining molten gold is poured into molds to form bars. After the molten gold is poured into molds to form bars, a sample is extracted to determine the gold and silver content. This sample is carefully taken and analyzed to assess the purity of the gold. Typically, the gold content in the bars ranges from 80 to 90%, indicating a high concentration of pure gold. Additionally, the sample is also examined for its silver content, which usually falls between 6 to 12%. These precise measurements help ensure the quality and value of the gold bars before they are cooled, weighed, stamped, packaged, and sent to a refinery for further processing. The smelting process of aluminum begins with bauxite, which is the natural ore used to make aluminum. Bauxite is a reddish-brown rock that is primarily composed of aluminum hydroxide minerals, along with various impurities such as iron oxides, silica, and titania. To extract aluminum from bauxite, it undergoes a series of refining steps. The first step in the smelting process is the crushing and grinding of bauxite into a fine powder. This process aims to increase the surface area of the bauxite particles, allowing for more efficient chemical reactions during the subsequent refining stages. The crushed bauxite is then refined into alumina through the Bayer process, named after its inventor, Carl Bayer. The Bayer process involves the digestion of bauxite in a caustic soda solution at high temperatures and pressures. This dissolves the aluminum hydroxide minerals present in bauxite, while leaving behind the impurities. The resulting solution, called sodium aluminate, is then clarified, and any remaining impurities are removed. Next, the sodium aluminate solution undergoes precipitation, where aluminum hydroxide is separated from the solution by controlling the temperature and adding seed crystals. The precipitated aluminum hydroxide is then calcined or heated to remove water and transform it into aluminum oxide. The alumina obtained from the Bayer process is a white powder that serves as one of the main raw materials for aluminum smelting. It is a highly stable compound with a high melting point, making it suitable for the subsequent reduction process. The smelting process occurs in a pot or reduction cell, which is a specialized container where the alumina is transformed into molten aluminum. The reduction cell consists of a steel shell lined with carbon material, acting as both the cathode and anode. The carbon lining is baked on site to produce large carbon blocks called anodes. To initiate the smelting process, alumina is injected into the reduction cell's electrolytic bath, which consists of a mixture of molten cryolite, a naturally occurring fluoride mineral, and other additives. Cryolite helps lower the melting point of alumina, making the process more energy efficient. In addition to alumina, pitch and petroleum coke are also introduced into the reduction cell. Pitch is a black, sticky substance that acts as a binder, helping to form the anodes. Petroleum coke, a byproduct of oil refining, provides the carbon necessary for the reduction reaction. Once the reduction process is underway, an electric current is passed through the anodes into the electrolytic bath, where the reduction reaction takes place. The electrical current causes a chemical reaction, separating the oxygen from the alumina in the electrolyte. The oxygen combines with the carbon anode, forming carbon dioxide, while the aluminum ions are reduced and sink to the bottom of the reduction cell as molten aluminum. The molten aluminum is periodically siphoned or tapped off from the bottom of the reduction cell and sent to the casting process. The smelting process continues continuously, with alumina continuously fed into the reduction cell, and spent anodes are regularly replaced. In Kitimat, the aluminum smelter consists of 4 buildings housing a total of 384 pots, which form a continuous line of electrical current. These pots are the heart of the smelting operation, where the reduction process takes place. Each pot is a specialized container made of steel, lined with carbon material to act as both the cathode and anode. The anodes used in the pots are crucial components of the smelting process. These anode assemblies are made from baked carbon blocks. Carbon blocks are produced on site in the carbon cell facility and undergo a baking process in a dedicated bake furnace. The anodes are baked at temperatures of up to 1,200 degrees Celsius for about 20 days. Over 600 pre-baked anodes are produced daily to ensure a continuous supply for the smelting operation. The anodes are transported to the pot rooms where they are installed in the pots. One notable aspect of the Kitimat facility is that the anodes can be changed without interrupting the ongoing reduction process. This is achieved through a well-coordinated system where spent anodes are replaced with new ones, while the smelting process continues seamlessly. This uninterrupted operation ensures a continuous production of molten aluminum, maximizing efficiency and productivity. The modernized facility in Kitimat is characterized by its high level of automation. The smelting process incorporates the latest technology and equipment to improve efficiency and productivity. Automated systems monitor and control various aspects of the operation, including the injection of alumina into the electrolytic bath, the feeding of anodes, the control of electrical current, and the tapping of molten aluminum. This automation reduces the reliance on manual labor and enhances precision and consistency in the smelting process.